my name is So from Hanyang University. Today, I'll present our work, Superficial Success versus Internal Breakdown. The main question is, when an adaptive MAS gets the final answer right, does that mean the agent actually collaborate well? Our answer is not always. Adaptive multi-agent systems utilize agent roles and communication structures for a specific task. Although these systems are built from general-purpose LLMs, the learned topology can become highly specialized to the training domain. This creates a problem. If we move the same topology to a new domain, the final answer may still be correct, but the internal collaboration may fail. Agents may ignore their roles, ignore messages from others, or solve the task independently. So, final answer accuracy alone is not enough. We need to check whether the collaboration process itself is reliable. To test this, we used a domain transfer setting. First, we train an adaptive MAS on a source domain. The system runs the agent roles and communication links from limited task-specific data. Second, we freeze the learned topology. Here, topology means both roles and nodes when communication links or edges. Third, we apply the same topology to a different target domain. This allows us to ask two questions. First, can the run topology transfer to a new domain? Second, even if the transfer in terms of accuracy, do the agents still coordinate meaningfully? We evaluate two representative adaptive MAS methods. The first is A-flow, which builds communication paths in a bottom-up way. The second is agent dropout, which starts from a dense graph and removes redundant rings in a top-down way. We test them on 6 domains: legal reasoning, detective reasoning, multi-hop, scientific reasoning, math, and common sense. This diverse setting lets us examine whether a topology runs in one domain can generalize to very different reasoning tasks. Our first findings is topological overfitting. In this table, diagonal cells means in-domain performance, while off-diagonal cells shows cross-domain transfer performance. Many off-diagonal cells are red, meaning that transfer often fails. This shows that the round roles and communication rings are frequently overspecialized to the source domain. However, some transfer cases still look successful based on accuracy. Look at this. This leads to the key question. Is this success caused by real inter-agent collaboration, or it only superficial? To answer that question, we propose two internal metrics. The first is role alignment. It measures whether each agent follows its assigned role while staying distinct from other agents. The second is connection significance. It measures whether incoming messages are influential and useful for the receiving agent. If connection significance is positive, the messages are helpful. If it's negative, messages are influential but unhelpful. If it is close to zero, messages are little effect. This matrix allows us to look beyond final accuracy and inspect the actual collaboration process. Using this matrix, we find illusionary coordination. This means that final accuracy can be high while internal coordination is poor. For example, when a topology trained on the legal domain transferred to the science, the accuracy may look reasonable, but role alignment drops to 0.22, meaning the agent no longer follow their assigned role well. Connection significance alone reveals breakdown. Rigor-trained topology shows negative connection significance in many target domains, which means that agent messages become unhelpful or not used meaningfully. So a correct final answer does not always mean that successful multi-agent collaboration. Sometimes individual LLM reasoning hides the failure of the collaboration mechanism. To conclude, multi-agent systems do not always generalize across domains. First, learned topology often suffer from multi-topological overfitting. They become too specialized to the source domain. Second, high final accuracy can hide poor internal coordination. We call this illusionary coordination. Therefore, auditive MAS should be evaluated not only by accuracy, but also by internal coordination quality. The main takeaway is that generalizable MAS needs both strong performance and reliable coordination. That concludes my presentation. Thank you for listening.